Okay. Hi, everyone. I cannot see any of you, so let's get started. I am Spiros. My US name is Nathan Brown. And may have to move this a little bit so you can see behind me what's happening. Okay, good. So I am a mathematical physicist at Caltech. Thank you. People who probably don't know what that means, but it's a little bit of a rarity to be a mathematical physicist. It's kind of like you need to get a mathematician and a physicist to go on a second date together and then to give birth to one of us. And this doesn't happen often because physicists usually hate math, right? And mathematicians just hate everyone. So we're here to talk about time, but from the perspective of a quantum physicist. That's me. So you probably don't know what time is, even though you think you do, right? But we'll spend some time on this. And I will walk you through it slowly. They told me I had about an hour and 15 minutes to do this. And I promise I will end on time. The whole presentation is about time. So let's start with this. I want you to tell me, by shouting, what do you think I will be playing here in this video? It's not Arkanoid. Wait until it finishes. Wait for it. Boom. What was that? Any ideas? Any guesses?
Light?
Yes. Who are you? Who brought you here? Thank you. You ruined my surprise. So this is actually light. And you don't get any candy. This is a femtosecond pulse of laser light. Who knows what a femtosecond is? Who are you people? This guy. Please tell me.
Science communicators.
Wonderful. So a femtosecond is?
A very short period of time.
Very short period of time. I think it's 10 to the negative 15 seconds, okay? Very, very short. Now, to be able to see something that fast and that short, you need the fastest camera in the universe currently, okay? Raise your hand, even though I probably can't see you, if you've ever watched any YouTube videos by the slow-mo guys. Yeah, okay, that's pretty cool. So the fastest they've ever been able to film with their own cameras is about 343,000 frames per second. A regular movie is about 24 frames per second. If you're Peter Jackson and you're filming The Hobbit, because you're going to be like a badass, then you do it at 48 frames per second, okay? And you look like resplendent as beings of light, because you get a lot more light with twice as many frames per second. Now, this gentleman, they went to Caltech. Believe it or not, this is where we have the fastest camera in the universe, at Caltech, which is just around the corner, okay? Not Cal Poly, by the way. It's very similar, very close, but different. So at Caltech, there exists a camera that can capture 10 trillion frames per second. Yes. Wow, right? What I showed you isn't even the fastest setting. They were kind of lazy and they filmed this at 100 billion frames per second. And you're seeing something that looks like a little like ball of light with ping pong ball, you know? Boom, 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 boom. And the actual scientists, they created this little thing that you see that they've drawn around there with mirrors. And that beam of light is probably just still going around there forever and ever. But what is interesting about this is that at 100 billion frames per second, they filmed for 1 second what happened, right? How long do you think this footage is? How many hours? It's 132 years, okay? I'm saying this because if you're living at that frame, right? Not the 24 or 120, which is about the fastest we can perceive what is going on in the universe, before anything happened, okay, you'd already be in your teens. This is what is going on here. The oldest person, Kane Tanaka, Japanese lady, 116 years old, wouldn't have made it to the end of this. After 1 second of this beam of light going around. And I'm going to show you closer to how we perceive the world, but imagine if we were a little bit slow. Okay. Now, I want you to notice a few things. First, his right fist, okay, is telling the guy, feel my wrath. His left hand is like, dude, stop being so dramatic. I barely did anything to you. But at this frame rate, whole universes within the quantum realm have already happened, appeared and disappeared, evolved. The whole thing that we call the laws of physics have had time to crystallize within a single frame that we perceive. So what we're really missing is pretty much everything. The way we do science, this is a science show, right, is we observe the universe, we take notes, and then we try to predict from the patterns what's going to happen next. What I just showed you kind of tells us that we're missing about 99.99999999999% of what is really going on. Right? And scientists at Caltech and at other places are trying to get to a place where we can get to see a bit faster, a bit more. It's pretty amazing. But this is at 1 frame per second. So then the question is, what is a second? Raise your hand if you think you know what a second is. Oh, I can see you better now. It's amazing. Yes? You don't have to. I will not ask you to tell me what a second is, so you can raise more hands. Wow, only 2 of you know what a second is.
We think we know.
Yes, correct. Because I bet you don't know that the answer is this. Okay. The second is 9,192,631,770 electron bounces between the 2 lowest energy levels of a specific atom, cesium-133. This is really what a second is. And this is what scientists decided the second would be 1967. Because before that, how do you think they decided what the second was? They looked up at the sun, right? And it was like, all right, how long does it take? It was the ephemeris second. How long does it take for the sun to go up and down and come back around and all that stuff? Kind of ancient. So how exactly do you measure these vibrations of the electron? Here's some equations. Here's a beam of laser light, okay? This beam of laser light starts at about 9.2 gigahertz. That's about billion cycles per second. That's the wavelength of the light. And you may not know this, but the different colors that we perceive in the world literally correspond to different wavelengths of light. That's it, right? And there is many, many wavelengths from the infrared all the way up in high energy to ultraviolet and X-rays and beyond. And we have a very small range that we get to perceive light that is coming to us because of how our retinas work. But what they did is, back in 1967, they took a laser beam and then they locked it into a bunch of cesium atoms that they were pushing through a chamber. And then if they got really close to the energy difference between the 2 lowest energy levels of the cesium atoms, what happened is the laser would actually hit the electron, excite it to the higher energy level. The electron then very quickly would come down, chill to the previous energy level where it used to be because it wants to be its lowest energy, and then by doing that, it would poop out another electron of exactly the right frequency, right? Which was exactly the energy difference between them. And so they did that in a feedback loop to try to see in the detector how many of these cesium atoms were actually getting excited. Again, fitting this back and trying to figure out exactly the energy, kind of like spectroscopy if you've heard of that before, right? Trying to figure out exactly, what the energy levels of this atom were. And they're so precise that this is what we use to this day to tell what time it is. Okay. 30 years later, they're like, oh, there have been some issues with using the standard. And the problem is that there are things that can change the energy difference between the two lowest energy levels of a cesium atom. And if you do that, right, then your second would actually change. Because the wavelength that you need to shoot, right, of laser beam at a cesium atom to try to get them excited changes. And then you end up counting different stuff. So if it is not at 0 Kelvin, which is like absolute zero, right, no, lower temperature, then you have everyone else coming around and like trying to shake hands with the cesium atom and say, hey, how are you doing? There's like, that's what temperature, by the way, is, right? If you want to know what it is, it's a thermodynamic quantity. It's an emergent thing. It doesn't really like exist. But if you zoom out, it tries to capture how many relationships this particular like system has with everything else around it. And if it is completely isolated, we say it is at 0 temperature. Okay? It can be itself, finally, right? Now, why at rest? If it is not at rest, then have you ever heard of the Doppler effect? Raise your hand. Right? When you hear an ambulance like, right, go by, it's the same frequency of the siren, but as it's coming towards you, right, it's getting like faster and faster somehow. So higher, like smaller wavelength, but as it's going away, the wavelength is attenuated, it gets longer and longer. The same thing happens here. And so if the cesium atom is moving away from the laser beam that is trying to measure this, it sees a different effective energy. And if it's moving closer, it sees a different one, right? So, time for audience participation. What would happen to 1 second if the energy difference between the cesium atoms of the two lowest energy levels increased by 25%? So you have the two energy levels of the cesium atom, and then you just bump up that energy difference by 25%. Do you think you will get exactly the same counting of a second as before? You're going to get more seconds, or you're going to get fewer seconds for you? More seconds, fewer seconds. Yes. Here's the answer. It's going to be shorter by 20%. Okay. Think of it this way, right? Imagine that the energy difference doubled. Okay. Then what you would actually need, the frequency of the laser would also need to double to get the same like cesium atoms to get excited. Which means that in half the time, they've already completed their 9.192 billion like oscillations in half the time. So twice as large energy difference in half the time. What this means is actually going to blow your minds, okay? It means that if for whatever reason, and we'll discuss some of these ways, your own biology, right? The things that make you up, start, splitting their energies or moving them to twice as much as they used to be, or 10 times what they used to be, then you're moving relative to everyone else 10 times slower through the world. You are time traveling to the future. Because 1 second for the rest of us is 0.1 second. It's just 1/10 of a second for you. You've already completed your required like 9 billion whatever transitions in 1/10 of the time. This actually is what is going on. You will come back 10 years later, if you were like, accelerating somehow, and this was happening to you, and it would be a century for us. You'd have skipped 90 years. And that's because of the definition of a second. This is how we have to have clocks to measure time. It is as simple as that. And the very best we have currently, and we're getting to better ones using better quantum physics, are these things. So how to time travel to the future? Rockets, you need to accelerate. When you accelerate, what you effectively are doing is you're literally shifting these energy levels, as I was saying before. The other one is try to not get sucked into a black hole, but stay close. The same thing is happening. Okay. Effectively, you're being accelerated very, very strongly near that black hole. And again, it shifts your energy levels. And relative to everyone else who is more stationary, you're now aging at like 1/10, 100th, potentially, of the rate of everyone else. And my favorite, and also the most realistic one, and the one that has gotten us the furthest into the future so far, is Back to the Future. We're still trying to reverse engineer the hat at Caltech. Okay, so we think that time is this one-dimensional entity, okay? And there's different frames, and we just move through it, right? So what is going on right here? We have a bunch of zeros and ones, and you can read them if you want from the top row all the way down. And each row encodes, in binary, as we call these zeros and ones, a different frame of a movie. And as you're playing the movie, you're just moving down this sequence of zeros and ones, right? It's a one-dimensional flow. Who decided that it cannot just be from left to right? You still have zeros and ones. The columns of this matrix, this is literally the matrix, by the way, okay? It's just not in green. So why not look at the universe and decode it as columns? The information is this way, moving this way, instead of like from up, down. Why not down, up? Why can't we just permute the different rows? Maybe like you're going to jump from the first one to the fifth one, to the fourth one, to the seventh one, second, third, and so on and so forth. Who decides that? Well, okay, there's someone who decides that. So the question is, if we can figure out who decides it, maybe we can tell them to stop deciding that, right? So is it possible to travel back in time? We know we can travel forward in time, as I showed you before, right? But it seems to be much harder to travel back in time. And the Avengers all know this, by the way. I've talked to them. So fill in the gap. To travel back in time, you need to fight against the thermodynamic something of time. No. What?
Demons.
Demons, entropy. The correct answer, anyone?
Arrow.
Arrow. Who are you people? Okay. I don't even know them, by the way. My own friends and family are here, and they don't know the answer, okay? It's embarrassing. Yes, the arrow of time. How many of you have actually heard of this? Okay, good. I'm depressed now. So this is what the arrow of time is. You start from a state of the universe, of the full universe, at time t. This is some heavy math right now, okay? And then there's an arrow that takes you from that state to the state at time t plus delta t dt, right? The next moment. We think of it that way. If you didn't take calculus, that's better for you. And then from that one, there's another state, and it tells you, that thermodynamic arrow of time, that you're going to be stuck moving closer and closer to some state that is like the final state. Right? You can think of it at the heat death of the universe, but it can be a lot of different stuff. Call them usually thermal states, okay? But you're stuck moving this direction. And if you think of it that way, then time is a different kind of beast, right? It's not just like you're moving in one dimension. It's like you can only transition from one type of state to another type of state. And the arrow happens to come from something called the second law of thermodynamics. Okay. So, what is the second law of thermodynamics? Yes, you're willing, you can answer this if you want. Anyone else? Go for it.
Entropy in a closed system can never decrease.
That's my friend Sai. Thank you. Even though I didn't even tell you the answer, but this is great. I have smart friends. So yes, the second law states that in an isolated system, the total entropy can never decrease. Which begs the question, what is entropy? Chaos. Beauty. So, entropy is a measure of the number of microscopic states that all give rise to the same macroscopic state when you kind of squint and zoom out. Okay? This is profound. This is very profound. This is the most important law of physics of them all, right? Including quantum physics, by the way. I claim that this is the very foundation the source from which all other laws of physics come from. And this is not a law of physics, it's actually a law of mathematics. It tells you that the thing that you expect to happen next is the one that has the most underlying possibilities, right? Because the universe doesn't care that you're looking at it from this point of view. It also exists at different levels, right? And if there's a million ways for something to appear to you one way versus one-to-one, which one do you think you're going to most likely see, right? The one has a million ways to happen at a deeper level. That's what this second law of thermodynamics tells you. So you always move to states that are kind of like that. Okay, so we're almost done. All things are possible in the quantum realm is what I told Paul Rudd, and he bought it. And then he told Kevin Feige and the Russo brothers, and they're like, we can time travel now. It's like, woof. But the answer is yes, you can time travel if you go to the quantum realm. And you may think, well, you can do that because you can always kind of like undo the second law of thermodynamics. If you get really small, you become microscopic, then you don't have to worry about like this difference between like many microscopic things to a macroscopic thing, right? You're already there. You can choose, right? No, it gets far worse down there. In the quantum realm, you don't just have one arrow of time. You have an infinite number of them, and they're all pointing in one direction, which is the following, that you are going to become useless, okay? The only way for you to move forward is to really become something that is completely useless to anyone else around you. It's kind of comforting, actually, you know? It's not your fault, right? So the quantum thermodynamicists, they call these states Gibbs states, thermal states, but really their true name is passive states. They're passive, they can't do anything anymore. You can't extract information, energy, anything, right? Like Nathan Brown. So, but there is good news. And this is the best part that most of you probably don't know, right? We have uncovered recently something very amazing. Space and time are not what they seem. Okay, there is something underlying both space and time. It seems that space-time is a hologram. So what you're seeing there is a representation of that. The red dots, right? These are points in space. That's where we are, different points in space. These blue pentagons, they're literally portals to an underlying reality, a network of entanglement superhighways. And how you move down there, if you can like open that portal and go underneath in that subspace, and we can do that, the way you move is by teleportation, which is cool. Okay, this is the only way you can move. You don't even go to or wherever you go, right? You teleport the information, and then when you look up at our level of emergent reality, it looks like things are kind of like moving from one state to another one, from one dot to another one, right? You're infecting with your state, with who you are, the next one, and then the next one, and so on and so forth. But it gets weirder, okay? I heard somebody laugh back there, but that's because I kept telling them, but it gets deeper. And it is true, because these black edges, the entanglement ones, right? When you push them all the way to this boundary of reality, where the red dots are, you see these white dots? You do, that's good, okay. This is where everything actually happens. We are a reflection of whatever input is put into these white dots at infinity, at the boundary of a universe that underlies ours. Whatever you put there travels that information via teleportation through these black edges, and then the portals work two ways, these pentagons, right? They bring it up, and then when we observe stuff at the red dot level. We don't get to see usually what is really going on underneath. But this is all hiding underneath, right? So how can we travel backwards in time? I'm going to end with this. Remember that world at infinity. These are the white dots, right? If we can manipulate what is going on there, then we can create whatever reality we want in the bulk, right? And by the way, I didn't tell you this, but in the bulk is where gravity exists. In that boundary, there is no such thing as gravity. We are a hologram of a universe with no gravity. That's pretty awesome, okay? You can fly there.
And that's a good cue to say, what the heck? What are you talking about? We need to ask you questions because
All right.
you blow our minds some more. So, do you want to finish this?
I'll do a very quick one.
Let's do the Q&A. Well,
Okay.
I'll come out for the Q&A,
Sure.
and you give us this last one.
Okay.
We have to be out by 9:30, so we want to get...
Told you it's going to be on time. All right, I can actually, yeah.
Oh, no,
Use the
keep
thing.
the projector up.
I thought it was going to be Oscar music. Okay. So I don't know if we're going to, maybe I should sit over there and then I can still click if you want to know how to time travel.
How to travel back.
You all came here for this, right? So this is in 5 easy steps. The first one, right? You realize you can't escape that final state, right? You have to move towards this, like this infinite hours of time are taking you to this special state. And that is defined by the environment and your interactions to it. So obviously you use spin particles, they take you to the quantum realm, which is that world underneath, as I said, right? You generate a new boundary. You put your own stuff at these like white dots, okay? Of course, you do compute the eigenvalue of an inverted Mobius strip, but they can ask me later. This is not even funny. This is real, okay? You have to do that. And manipulate the new environment. You create like a new physical like, state in the bulk of it that pushes you back in time to whatever time you want to be. Then you disable that artificial environment. The universe tries to heal itself and reconnect, right, with whatever the environment is supposed to be for that particular bulk state, which is the rest of the, 1970s. And that's it, right? So I just want to end with like a pitch to, if there's any Disney executives here tonight. Just leave it there. And thank you all.